Okay, we're going to look today at 11.3, solving radical equations. Obviously, a radical equation is an equation which contains a radical, surprisingly enough. So let's look at an example. We have a radical, we have an equal sign, we have a radical equation. Now, this is really no different at all from what we've been doing, solving linear equations throughout the year. We have to get our order operations right, so we refer always to PEMDAS, and remembering that when we are undoing equations, when we're doing inverse operations, we are reversing our order. So what is happening to the variable? There's a square root, which is essentially an exponent. It's being multiplied, and there's a subtraction. And that's the order that it's happening in there. Now, the inverse operations, we have to have the inverse of a subtraction is an addition, the inverse of the multiplication is a division, and the inverse of the exponent is also a kind of exponent. Okay? And the order that happens in is like that. So we'll do that very quickly. First of all, we adding 8 to both sides. We then divide by 2. And we then square both sides. And obviously the squaring both sides comes from, if you square the square root, what you're doing is you're multiplying it by itself, and that is the square root of x squared, which is obviously x. We remove a square root by squaring that component. So there we go. Fairly simple problem. They obviously can become much more complex. Okay, again, we have to look and see what is happening to the radical. We notice actually that at this point the radical reveals itself as not just as an exponent, but also a form of parenthesis. If we look at what is inside the radical, this is essentially in parentheses, so that is going to be undone last. Essentially, that anything inside the parenthesis is locked in there until we get the radical isolated, and then we can square it. So let's do our inverse operations. The first thing we're going to do is subtract 12 from both sides. We then divide by 4. At this point, we square both sides, and then we finish off. Okay? Nothing particularly difficult there. It's a little bit unfamiliar, but it's straightforward enough. Sometimes we'll find that we have radicals on both sides of an equation. But this is easily done. We square both sides. And we are then left with a fairly simple problem. With no mystery about it. Okay. All right. I think the things to do now is to work through some problems. These are on page 7 3, 2, and there's a section there, 3 through 20. Okay, I should just include them here. All right, plenty to be getting on with. Do as many of those as you feel necessary until you're comfortable with these kind of problems. I don't think there's anything there which is going to present too much of a challenge. So once you've completed this and you've checked your solutions, we'll come back to the recording and we'll move on to the next variant. Okay, we're going to look at what we call extraneous solutions. Let's look at a very simple one first of all. Square root of x plus 13 equals 0. We go ahead and try and solve this. We encounter very quickly a fallacy, something which cannot be. The square root of x cannot be a negative number, and we can easily say here there is no solution. But it's not always that obvious. Let's try an example. Let's try this. We square both sides to remove the radical. We then get a quadratic. We'll rebalance it. We get that x squared plus x minus 6 equals 0. This is relatively easily factored. Looks like plus 3 and minus 2. And we can then apply the zero product property. And we get our solution. So far, so good. However, if we try and put these solutions back into the original problem to see if they are true or not, we get this. So we have a negative number, which is a square root. We cannot have this. So this, in this case, negative 3 is an extraneous solution. We'll try 2. If we try that, we get square root of 4 equals 2, and that is correct. So in this case, while there is, even though it's a quadratic equation, which normally has two solutions, and we get two solutions, we in fact find that one of those solutions is extraneous, cannot be. So there is only one solution to this quadratic equation. Okay, right. The problems relating to this are on the same page, 732, and there are some problems there, 22 through 27. I shall include them here. Okay. Right. Well, I think that's probably it for the basics for this topic. What I'd like you to do now is to work through some of the word problems starting on page 733. I'll do the first one right now as an example, and you can then work through the rest and in your own time for the rest of the lesson. So I think we'll start with, is it question 31? Let's have a look. No, it's question 36. Sorry, got that completely wrong. Okay, so it's a map of Texas, and there's regions of heavy foliage, etc. They give us an equation, radical. In fact, it's a function, a radical function, y equals 2.5 root 143 minus x. X is the number of years since 1907. In what year were about 20 million acres of land covered? So there we go. Now Y is, the units are millions of acres. Okay. So let's work through this problem. So Y is 20 million. The units are already millions, so we just put in 20 equals 2.5 square root of 143 minus x. Okay, let's work through this. 20 over 2.5 equals the square root of 143 minus x. We square both sides. So 143 minus x equals 20 over 2.5 squared. X equals 143 minus 20 over 2.5 squared. And if we work that through, we get that x equals, that gives us x equals 79. Let's look at the question. What year? So number of years since 1907. So 1907 plus 79 equals 1986. The answer to the question. Okay, great. Well, that's that. Work through the rest of the problems, check your solutions. Your homework will be 12.3c, which will be, 11.3c, which is up on the desk and is being distributed to you now.